All right. Okay. So, yeah. Hello, everyone. Before we get started, I just wanted to quickly introduce the hydrological loading working group and to everyone. So, this is this group is called Hydrological Loading, Measuring and Modeling. It's part of IAG Intercommission Committee on Geodesy for Climate Research, or let's say ICC in short. And the focus is basically on using geodetic techniques to measure and model hydrological loading. So we are about 25 to 30 members from different parts of the world. And one of our activities hosting webinar with invited speaker. So, and 2 days is a special day for us because it's our first webinar, public webinar. And we are really happy to have Fabrice Papa with us today. Thanks a lot, Fabrice, for agreeing to give a talk. So I think most of you already know Fabrice, but for those of you just getting into altimetry and hydrology, Fabrice is research director at Lagos in France, and he's been working on understanding the water cycle using the geodetic satellite observation and hydrological model. And I know Fabrice from SWOT Science meeting and several SWOT working group. He's a member of the SWOT science team. So he got his PhD in 2003 from French Space Agency and the University of Toulouse. And he spent time at Columbia University back in 2010. So the talk today will last around 40 to 45 minutes, and then we have up to around 15 minutes time for Q&A. So feel free to drop your question in chat during the talk. So MJ and I will read the questions during QA, and if you like to ask your question yourself, please raise your hand, and I will unmute you so you can speak. So okay, so looking forward to your talk, Fabrice. It's over to you.
Thank you.
Yeah.
Do you see my screen properly?
Yes, you can.
Is it moving?
Still not in
Perhaps
full
you want to do
screen.
it full screen, right? Yeah.
Do you see full screen or not?
Not yet.
Okay. Now?
Not
No.
yet.
Because to me, it is full screen for me, so I don't understand. Okay, let's. Because I cannot see what you're seeing, because for me it's it's full screen.
Do you have dual monitor, perhaps? So you want to? Do you have two monitors working together?
No.
The single monitor.
Yeah, the same one.
Yeah, just check out the share button and see we are sharing the same correct screen.
You know?
Often helps when you reshare, stop sharing and share again.
Yes.
That good?
Works. Nice tip, MJ.
Okay. Let me clean the windows also, because now they're hiding everything. But anyway, let's go. Okay, thank you very much for inviting me today to give this first talk on the seminar. But I had a feeling we made many seminars before, but maybe this one is special, or it's a new session. So, and today I will talk about how can we measure storage more than fluxes. Today I will focus on storage and how they vary at the basin scale or globally. Using a satellite. So this is kind of current advances and future opportunities that we can have from tracking these surface stores from space. So we come back on the fact that water is a major scientific and societal issue, and it's a vital resource, but it's limited. And we all know that it is very important. And if we gather all the water on Earth, like, and we put it in the sphere. It is like the sphere above the USA, which is the diameter of only 1,500 kilometers. And if you extract from that the fresh water, it becomes only 300 kilometers in diameter, and that's the one on top of the North USA. But the fresh water, which is available to humans, becomes this tiny little drop over Florida. And over the continental water, if you remove Antarctica and the ice sheet, they are only 1% of the total amount of water on Earth. Now, of course, they play a critical role in the continental water cycle and the climate system. They are critical for many purposes, especially life on Earth, the health, the activity of the human and their environment. And they play also a key role in all the global and energy cycle and the way they interact also with the climate system and how it varies. So there is, of course, a key need to measure water resources, and it's very important for the governments and the society. So myself and the people I collaborate with, as scientific questions, we have such question we try to answer is how the water resource availability varies at different scale, temporally and spatially, and also how do they interact with the climate variability, now climate change, but also the anthropogenic activities. And you will see, so I'm going to introduce some regions that we are really focusing on our work. So the question that we are trying to answer, they are important globally, but in our work, they are more specifically important to the tropics and two major basins that we are continuously studying, which are the Amazon basin and the Congo River basin. So combined, these two basins represent between 20 and 30% of the total water, fresh water, which is discharged annually from the continent to the ocean. So this tells you the importance they play on globally. So the Amazon is about 6 point something million square kilometers, while the Congo is a little bit smaller. It's about like 4 million square kilometers. So these two basins, they are really relevant on the local scale, but also globally, since they play a key role both on the water resource and the biodiversity. They are also impacted, but differently, by human actions. That's why they are important to study jointly. The Amazon have been known for many transformations in the last decades due to dam deforestation, mines. And let's say that the Congo is a little bit more pristine, but is now experiencing such large changes because of its exploitation. And these two basins, they are now vulnerable to climate change, and especially what we call extreme events, where Science made the first front page of his magazine last year, where the Amazon is experiencing the fact that wet gets wetter and dry gets drier. So we go towards like more extreme flooding and more extreme drought. So therefore, there is a need and more to understand and forecast freshwater resources, their availability, and how they will probably change under global change. So we all know this. We had many presentations regarding that. The way we observe the water cycle, historically, we made it with traditional gauges that can measure like various parameters of the water cycle. But the distribution is unequal globally, and also there is a decline in the amount of observation of the hydrological cycle, for instance, the river discharge. And this is another example that I like to give over the Congo River basin. So when we say that it was not monitored, this is not completely true. Before the 60s, they had like dozens of gauges that were measuring water level height and discharge over the basin. But this is the dramatic current situation. This is the second largest river basin in the world, has only like 10 to 12 gauges which are in operation lately. And plus, despite the fact that there is a decline in the observing system, in situ, they have difficulties to measure certain phenomena, such as large flood, especially in remote areas, such as you have in the tropics or in the northern latitude. So for that, we are using satellite to complement this in situ observation. So now we are capable to characterize and study some hydrological variable from space using various satellites. And we are able for the past decades to try to understand and quantify water quality, water quantity, and how this variable are changing over time, over space at different scales. And there is a growing number of the use of space hydrogeodesy, which is the main interest here for this group, and the study to and the use of this data to study water and the related science. So this is a figure that I extracted from a recent paper from Fernando Jaramillo that was published last December, that really show like the growing number of the use of satellite to study various hydrology components, so from the ice to the groundwater to the water storage, the soil moisture, and by the various hydrogeodesy technique that goes from GNSS, gravimetry, INSAR, or altimetry, and how there is an exponential growing actually in the use of this technique to study these parameters. And this doesn't count, we will see later, the launch of the SWAT mission, which is expected to revolutionize the way we see hydrology, at least at the surface. And we had many presentations in this group, I remember, with the use of INSAR or gravimetry or GNSS to study hydrological loading. So I will pass on that. This is just to illustrate one of the most famous and long-term technique to study the total water storage over the continent using GRACE. We all know this. But there is the storage on the river, which is still not very well measured. And I think that could be a real growing interest for the community, which is interested in the hydrological loading. So this is a figure, I won't go too much into detail, which is extracted from a paper from Collins and Cedric David and colleagues last year, which shows like how much water are stored in rivers depending on the resident time that you take in various models. So you see that the estimate we have now, they are largely spread, but between 3,000 and 4,000 cubic kilometers are stored in rivers and are evolving over time like that. So it is really like a key parameter to measure. And if we go back to the basin scale water balance equation, the storage variation in time is linked to the precipitation, the evaporation, and the discharge. The total water storage that we know, its variability, can be decomposed in three other components, which are the surface water, the soil moisture, and the groundwater. And all these quantities still in 2025, we have highly difficulties to quantify it, to measure it. And as I will present in the following, at the global scale, we mainly only have crude model estimate, as I show from the paper from Collins, which are giving like very large spread of quantities measured from this model. So we have problem in the three reservoirs: surface water, soil moisture is measured, but it's really most of the time only the few centimeters from satellite. Otherwise, it relies also on model. And the groundwater is even unknown, because for that, we will see that we have to combine all the data that I've been talking. And we also add the uncertainty when we want to derive groundwater from all these satellite measurements. So for this, obviously, only one technique is not going to work, and we really need to work towards an integrated approach that merge satellite data modeling, but also in situ. So quickly, I will go on the few variables that we know how to measure very well from space. So this figure is extracted from a paper from Fassoni et al. In 2021 that reviews like the technique which are available to measure some hydrological variables over the Amazon. The idea of this paper was double. It was to show how the Amazon also contributed to the development of all this technique. So it is like a gain development. Thanks to the satellite, we gain a lot of knowledge about the Amazon because a lot of studies were made. But all these studies were also developed because of the Amazon. So that was really like to show how the Amazon basically became a laboratory, an open air laboratory to develop a lot of satellite techniques, and including three that we are familiar in our community, which is the surface water elevation from satellite, river discharge that we tried to measure, but until SWAT we didn't have direct measurement, and the terrestrial water storage. So I will present now techniques that we have been trying to develop over the time to characterize surface water storage variability. We don't have direct measurement of surface water storage variability. SWAT is supposed to provide us some estimate and quantities, but it will take time to develop that. However, for the past decades, we have some complementary satellite observation that could help us if we merge them adequately to characterize some of the variation of continental water storage. So the approach is to use a combination of satellite altimetry, which are providing water surface elevation, with other datasets which are providing the variation of the extent of water over the surface. And in our case, we use, because we are so interested in the long-term variation of this variable, we're using one of the only satellite that one of the only techniques that provides such measurement of the surface water extent variability at the global scale and over the long term, which is called the Global Inundation Extent from Multi-Satellite, which is the GIM product. I will develop on that a little bit longer. So for the moment, it hasn't been tested, but I think for our group and for hydrological loading, knowing the variation and the variability of this surface water is very important because it can contribute to this hydrological loading. So that's why I'm going to introduce the way that we are trying to characterize this, and maybe it can create some interest in how we can use that in our group. So first, I will present quickly how we measure surface water level from space and the variation, and the use of radar altimetry over continental surface. I know that we had already some previous presentation, but quickly I would just remind that the altimetry was initially designed to work over the ocean and measure sea surface height variation. However, quickly it's shown very high capabilities over water bodies and in the continent. So I won't go into the technique. We all know that how we calculate the water surface elevation from altimetry, calculating like the range and putting this into reference to ellipsoid and using like many corrections to adequately have a water surface elevation. So many satellites over the last 3 decades are used to do this. And we create over the continent what we call a virtual station, which provide the water elevation of the surface at a different interval sampling, which is linked to the satellite. And that can go now from 10 to 35 days with like intermediate, like time range. So a virtual station is built like with can be built automatically or manually. We use like several trackers. I'm not going to go into the techniques, but the idea is that there is now a possibility and using multi-mission altimetry to recreate long-term time series at the same location with an uncertainty that depends on the satellite we use and the tracker and the technique, which range from 5 to 10 centimeters to half meter. So here's an illustration how we built a virtual station over the Amazon and this comparison with in situ. So it's a little bit of vintage also image, but I like to keep this one because it was one of the first. We have like much more better illustration now, but this one of the Amazon was one of the first one made by Silva et al. In 2010. And at the bottom, the image, it's more like a more recent one made by Benjamin Kitambo during his PhD, where he's comparing here long-term multi-mission satellite altimetry derived water elevation over the Congo River and compared to in situ data. And that shows that, you know, now using like from 1995 from ERS to Sentinel-3, we have an uncertainty of about 20 centimeters, which is varying depending on the mission. So this is to illustrate over the Amazon. We have now like hundreds, even thousands of virtual stations over the Amazon that help us to characterize the dynamic of the river, depending on the season. And here you can see, so this is the median amplitude over the Amazon. So we can see that over this river, we have like amplitude which are higher than 15 meters. And in the headwaters, like a smaller stream. And you can really see the distribution of the maximum and the minimum of the months it is reached. Divided by the equator, so that's on the right. So there's hundreds of papers worldwide, and we talk about this in Europe already, that evaluate altimetry versus in situ. And I don't think we need to more prove that it's a very powerful instrument in complement with in situ, because we still have problem in getting high temporal frequency, but it's very powerful to study hydrological variable. So here's an illustration over Africa. Some variability over mini rivers from small stream to large stream over Africa. And you can see that we can now reconstruct a very long-term virtual station, and that provide a very important information, especially on the change and the long-term changes. At the global scale, this is to illustrate what we have currently with Sentinel-3. So we see that we have a good spatial coverage now that will enable, maybe we will see at the end, like to derive what we will do at the global scale. And this is what we have with SWOT now. So we know 2 years ago, almost 3, the SWOT mission was launched. And this is like the amplitude that we have using SWOT water surface elevation over 1 year, 1 year and a half, from 2023 to 2024. You can see that we have a much denser and finer coverage of the rivers that can be seen with SWOT. So this is an illustration of how altimetry can help to monitor water surface elevation during drought. On the map over the Amazon, that's the anomaly of the minimum in 2023 during the huge drought, as compared to what has been recorded as a minimum for the year before. You can see that sometimes during that period, which was very, very dramatic due to many factors, water level was sometimes 6 to 8 meters below what they used to below the normal in terms of minimum. So now that we show that we can characterize surface water elevation, if we want to get volume or storage of the surface, something that we need to quantify also is the inundation or the extent of the variability of the extent of the water body that we're looking into in the rivers. So in this presentation, I won't talk about the variation of water storage in reservoirs and lakes, because that necessitates like a completely and comprehensive other talk. So in my case, I focus more on rivers and floodplains, what is adjacent, the wetlands, not the lakes and the reservoirs. So as I said, there are many techniques that enable us to measure the extent of surface water, and they all have pros and cons, or there's always a trade-off. So of course, the famous one is using SAR, which is a powerful instrument because it has very high resolution, penetrates the clouds. Very famous also to measure the extent of water is the use of infrared and visible. However, it's very high frequency, very high resolution, but there's problem with clouds. So for many years, it was very difficult to have a global data set of measuring this. And the compromise was to merge different satellite observation. And this came the GIMS products, which make use of really like multi-satellite observation at different wavelengths to be able to detect water under clouds, to correct the vegetation, and to do that at the global scale over the long term. So GIMS is based on passive microwave, SSMI. So many different emissivity at different frequency. I don't know if it's true, but I read today. So the first of this satellite before SSMI was Simmer. It was launched in 1978. So you see like the record that we have. And I think I read yesterday that the 30th of June was the last record of the SSMI's satellite. NOAA is stopping it. So that's a little bit catastrophic. I don't know if they will record. I just read that NOAA is stopping. Like, so I would like to, if someone can give some, there's more information on the US side, if there are some people, but I found it completely, crazy. There's no other word, like such a long record of satellite from a Simmer to SSMI, then SSMI. And Catherine Prigent, my colleague, is still using all this data to update until 2024 now, this database. And I think such products are at risk if we don't have the observation anymore. But anyway, so we merge passive microwave from SSMI, active microwave, visible and near infrared into a classification that provide the fractional inundation calculation at the monthly mean, but also over 10 days. So this is an illustration of the GIMS product at the global scale. So here is the mean fractional surface water extent at the annual maximum. So for every year, we extract the maximum for each cell. And so the observation, they are mapped on an equal area grid of about 25 kilometers by 25 kilometers. So it's very crude resolution. That is also the trade-off, is that if you want to have long-term global, up to recently, you have to most of the time use this kind of sensor, which have very crude resolution. It is now, I didn't put it, so it is now available from 1992 on a monthly basis to 2024. So what it provides is that over each pixels of about 800 square kilometers, it provides a fraction of this pixel which is inundated. So you see when you have red, that means 800 square kilometer inundated. So the pixel is mostly fully inundated. And this is what you see in the major deltas of the world, like the Ganges, like the Mekong, or like all the central corridor of the Amazon. So of course it's a global project. At that time, there was not many ancillary data to evaluate. But the one of the main evaluation that we performed was over at the Amazon, where actually we concluded that the uncertainty of GIMS was about 10%, on the average. When you compare it with the SAR mosaic that has been extracted from the LoRaS paper in 2003. So I'm not going to go into details. Of course, there are a lot of disagreement on these two comparisons. So on the right, that's the wetland extent or surface water extent from GIMS. On the left, all in blue, this is the estimate from the SAR. Or you can see that overall there is a good agreement, but when you dig into that, of course, there are some differences, especially in the total amount of water which has been detected. Nevertheless, from what GIMS can see, which has difficulties to see under the vegetation, there is a good agreement, at least between the low estimate of the SAR and GIMS, and also what has been seen at the maximum by Peckel. So this is what you see in the red line. So overall, this slide, there are many evaluation that has been done, especially in the paper by Fleischmann et al. 2022 over the Amazon, where we compare everything which is available in terms of flooding, extent and occurrence over the Amazon. And basically, over the 50 products that we compare, they all, except over open water, they all disagree strongly. So the idea here is just to say that at the large scale, GIMS is probably not perfect, it's not the most accurate, but it works very, very well, especially that provide this over the long term and at the global scale. So the idea now that I presented two of these data sets is how you can merge them to get an estimate of the surface water. So as I say, like I'm not going to go into the technique of the interpolation that we did over the two data sets, but the main idea here is that we have many virtual stations, 100, even thousands. Here it was 1,200, I guess, over this first attempt. And we have the extent. So we have a variation of both variables, the extent, the height. And when you combine that, normally we can have a variation estimate of the volume, which is the combination of these two data sets. So we did that in 2012. So we combined both data sets that we had at that time to characterize the drought in the Amazon that the Amazon experienced, another extreme drought that was in 2005. So I'm going back. Yes, it is this. So before we get the volume, we had to distribute actually the water surface elevation of the altimeter over the map of the extent. So here, for instance, we create an anomaly of the minimum of water level over the Amazon. And that was one of the first maps that characterized the water surface elevation for all the rivers over the Amazon, where actually we merge really GIMS extend with the surface water elevation from altimetry. And then combining this, we could calculate at the global scale, at the basin scale, the surface water volume variation, which is here in the gray line. And we can see that we can estimate the variation over the time from 2003 to 2008 in this case of the surface water volume, which varies between 800 and 1,200 cubic kilometer per year. That's why we estimated using altimetry, and it was in good agreement with previous estimate in the range, let's say, that were provided by some models. And during this drought, we could estimate that the deficit in the surface water storage was 70% lower than the other minimum for the other year, which was very extreme. And when we compare to the total water storage measured by GRACE over this period, the surface water storage variation contribute to more than 50% of what was detected by GRACE. So this one was one of the first results that we had like that at the scale of the Amazon. And here, this is just to show that the variation were adequately represented as we compare in blue with the discharge of the river. So this technique over the year has been applied to many other basins by our group, but also by many other different people. So normally I don't like to put tables like that, but maybe it's just to keep, it's a part of a review paper that we did on surface water storage variability from satellite. So this provide not only with GIMS, but with all the technique we could gather and that estimate surface water storage from very small region to large basins, and to show that there are a growing interest in calculating this water storage for the large basin, but also for the Chad, and covering different environment from the tropics to the northern latitude, under flooded forest, when they use like SAR and over the floodplain, over the rivers. So overall, there is a good agreement in general between the techniques that we use. The only things that we don't really have is an agreement with the models. So here, this figure shows the relative contribution in terms of surface water storage as compared to the percent of the variation that has been recorded by GRACE. So here we present like some major basins and sub-basins, for instance, over the Amazon. So globally over the Amazon, 50% of the total water storage from GRACE is explained by variation of the surface water storage. And inside the Amazon, in terms of sub-basin, there are a big variability. This can be more than 50% over the central corridor, but it can be less than 10% over the Xingu basin. So all this depends if you have a large aquifer and if you have a lot of floodplains. Same over the Congo. You can see the middle Congo, which is known for the cuvette centrale, which stores a lot of water. In this case, over this region, more than 30% of the variation explains the total water storage variation from GRACE. So basically, in all the large basin where you have floodplains or large delta, such as the Ganges, Brahmaputra, or the Mekong, the contribution of water storage that we estimate, or that other estimate, is large, between 40 and 50%. But something that we have to see here also. So this is 4 years ago. Now there's been a lot of improvement, I believe. But in blue, this is the portions of surface water storage as compared to GRACE provided by models. And you can see that in the 4 that we gather over the Ganges, the Mekong, the Congo, or the Amazon, the model doesn't properly, adequately, we believe, provide accurate estimation of the surface water storage. For instance, over the Amazon, like it's less than 10%, when actually just we know by the variability that we have in water surface elevation, which are more than 50 meters in the corridor, it cannot be that low. So it's by this contribution of the surface water storage to the total water storage is highly variable among the basin, but among the sub-basin, and is often linked with, of course, claimed variability or geological features, and the models that we have at the global scale, they have difficulties in properly addressing this. So something that we tried also, once we had estimate surface water storage for the surface, it's to go a little bit behind that and try to get an estimate of the variation of the groundwater over a large river basin. So for this, we just use the fact that the variation in groundwater is probably linked with the observations that we have, the total water storage change from GRACE, also the soil moisture, that we can have from satellite, but here in this case, we mainly use like a combination, an ensemble of model or GLIM, because the satellite provides only over a few centimeters, and what we need here is the root zone. And our estimate of surface water storage. So when we combine all that and we subtract to GRACE the two other variables, we can try to do a full decomposition of GRACE total water storage over the Amazon and extract the unknown groundwater. So this is what we tried over the Amazon. And so that was one of the first decomposition from for the entire basin. So here it's using GIMS and the altimetry from 2003 to 2011. So in black on the top left figure, black is the total water storage variation. In blue is our estimate of surface water. In green is the one from soil moisture. For this figure, it's a combination of several models, mainly WGHM, ISBA, and another one that I don't recall now. And then we can extract like that in red the groundwater variation, month-to-month variation over the Amazon. And so one of the key results that is in agreement with what we find in previous studies is that the surface water to the total storage change from GRACE is about 45%. The soil moisture contributes to 25%. And therefore, the groundwater is about 30% of this total water storage variation. And on the top right, this is like the average variation over 1 year. So this is something that I talked already. So then we could, you see that the Amazon is made of major sub-basin, and here we made this decomposition over like each of these sub-basin. And what we wanted to show there is that depending on the geology and the characteristic of the basin, depending on the fact that you have a lot of floodplain of inundated floodplains, floodplain forest, the contribution is obviously we confirm that the contribution is very different. And inside a major basin like that, the contribution are extremely sparse, going from 10 to 50%. So this is a figure just to show in case we have questions, because we all have questions. Major problem that we always have. First, we don't have in situ data, and second, we don't have more in situ data to, in general, evaluate or estimate such a variable. It is possible with water level, it is possible with in situ discharge, but when you want to, over such a large basin, evaluate your estimate in terms of groundwater, the only stuff that we find is 2 wells, like in one of the Rio Negro region. But nevertheless, this is kind of, I hope it convinces you, given the fact that the difference also of what we measure between a well, which is a very point estimate, and our estimate of groundwater variation, which comes from GRACE, which has a resolution of hundreds of kilometers, combined with other several techniques, we found that the difference in terms of millimeter, but also in terms of timing, were quite astonishing. So this is the only way that we could partially evaluate our estimate. But this was the first map over the region in terms of the seasonal variation, but also the standard deviation that show the variability, that shows that in terms of groundwater, we really catch the features of the geological formation of the Amazon, which is mainly the big aquifer that we have in the central Amazon. Quickly, I'm going to introduce another technique that we developed to estimate surface water storage. Is the combination of GIMS with DEM. So I won't go into details. The idea, there is a publication that was released like 2 years ago. The idea is to combine DEM with GIMS by creating isometric curve. So I won't go too much into details. The idea is that to take all the elevation of a DEM over a region of the GIMS pixel, redistribute them into ascending order to create a bucket-like distribution of the DEM, and then fill up that with the uncertainty we have using the surface water extent. And from this, we did that over the Congo. We could create using that the long-term GIMS estimate the variability of the surface water storage over the entire basin. Here on top is the variation, and the second figure is the anomaly. And what we see is that the Congo River Basin, at the scale, has a variation annually of surface water storage that it can reach 120, 130 cubic kilometer. And that the variability is very high over the years. So here from 1992 to 2016, you can see that surface water storage respond very well to such climate variability, large scale phenomena. I didn't go too much into detail here, but the Congo experienced in the 90s to 2000 a very large scale drought that we could map here in terms of the deficit in surface water storage. So here is for the period December 2005, January 2006. There was a huge drought that we could see on the figure before. And this is the deficit in percent of the surface water storage over the long term. And we can see that the Cuvette Centrale experienced like a deficit of more than 40%. So this was published in the work of Benjamin Tambo 2 years ago. Why we did also this technique is that we believe that that's probably the only one that can help us to develop that at the global scale. Using altimeter and GIMS at the global scale to have that probably has too much uncertainty. So we believe that one way to overcome this is to develop this hypsometric curve using several DEM at the global scale. And this is a study that we are continuing with Benjamin and Mohamed. And hopefully one day we will conclude that. This is an example of a South America that we already made, providing like the mean variation of surface water storage over the region using this hypsometric curve approach. So in conclusion, there are now data sets that quantify surface and possibly groundwater storage from multiple remote sensing technique. We use them to understand process changes, the way groundwater and surface water interact, and they can be very useful. We did that especially with the MGB model to evaluate such a model and to improve them. They are also very useful to study extreme events, which show that we could characterize the deficit in surface water, which is very important. And these data sets are available. So if we can find a way that they are useful for the hydrological loading community, how can we transform this volume of water into something that can help us represent this loading? I believe there is something to investigate here. As I show you, up to now, we were more in the crude era with the satellite that we use for the long term, but we are now entering a new era of high resolution satellite, given the fact that we can process so much data now and that we have observation. So the perspective is probably to try after to derive such data set at a lower resolution. GIMS has been downscaled many times at up to 90 meters. The GIMS D3, there's a new paper that has been released by Lehner, Prigent recently. This is something we can investigate actually, to have a much finer resolution. Also merge this data set in a different way, especially to understand the driver. They are very important to support the development of model. And still test at the global scale the way that to combine this altimetry with the GIMS, especially using the densification of Sentinel-3A, 3B now. And why not combine this with the GRACE FO extension? This technique has been done locally or at regional scale. And I believe it's important that we keep our effort to do it globally. And of course, something that will support that is it's the SWAT mission. launched in 2022 at the end of it, but which was planned since 2003, and which in its objective should help us to estimate the variation of surface water storage, both in reservoir, in lakes, but also in rivers and floodplains. And for that, I finished the loop. There was a talk from Daniel like a few months ago, and he showed like the hydrological loading that he's doing with GNSS over the Amazon, how it can also help. So I think we have lots of tools. We saw many presentations last year from SAR, deformation. I think the goal of this group is we wanted to make a kind of review, recommendation paper, and hopefully what I present today can at least contribute a little bit or give idea how we can use that. Thank you.
Yeah, thanks, Fabrice. I appreciate for your great overview of the surface water. So like you said, with more and more satellites being launched for altimetry, we are getting very valuable insight into surface water, something that is very super useful, not only for hydrologists, but also for geodesists and even meteorologists and others. And as you mentioned, within these working groups, we are looking into different component of water component and how this kind of component interact with the crust and produce deformation, and vice versa, how the deformation that we are measuring through geodetic techniques can be inverted to calculate surface water and subsurface water. Thanks again, Fabrice. So now Q&A is open, and if you have questions, please raise your hand. I don't see questions in Q&A. Yes, there is
I have a question.
Yes,
Yeah,
I think Payman wants to ask question.
Okay, go Payman first, and then I can ask later.
Yes, Payman.
Did you add Payman?
Yeah, I think Payman can speak now. Oh, Mohammed, you can go ahead with your question. I can manage.
Fabrice, that was great as always. The GEMS data set was, of course, a very fundamental data set in terms of surface water extent. What would be the future of GEMS in light of having SWOT mission? Would you combine SWOT with all these techniques, or would you have two different parallel activities?
I think they can complement each other, but I believe if it can be extended, the big advantages of GEMS lately is its long-term record.
Mm-hmm.
So starting now in 1992, and which is now extended to 2024. So, we're almost reaching 30 years of GEMS, which is like even altimetry where we try to do that, over the Congo, when we can extend long-term time series like that, we reach maybe 150 points maximum.
Exactly.
GEMS provide that globally. So I think after SWOT can be useful, maybe for GEMS, for what has been done with other techniques is the plant scaling techniques.
Okay. So you would benefit from SWOT just to check the downscaling activities.
Yes, I think so. After there might be a way of merging both data sets, especially if I said if they have problem with SSMIs now, might be a good way to continue, because what is very important for us is to continue to record all this surface water extent. But they are measuring the same stuff, but very different way. And so, even globally, the extent of water with SWOT, with all this dark water problem, and what can you see below vegetation, up to what extent? I mean, there's still a lot of work to do to have the correct.
Indeed. And my second question goes to the modeling aspect that you have nicely showed and the mismatch between what you quantify with satellites and the models. So what's the perspective in that respect? Is there any activity, I mean, global activity to combine or improve the models in one way or another?
I think that's the way to say that, and I think that's what Cedric shows in his paper. You know, depending on the resident time, you increase the storage. The more you keep the water on the continent, the more you increase the storage. And if it goes too fast into the river, so I guess one of the main objectives of the model now is to at least reproduce accurately where is the water in the drainage basin and to what extent. Even localized, as I know, we've been working a lot with MGB model or ISBA over the Amazon and the Congo, where we have a lot of satellite information, but still it is not properly. The floodplains of the Amazon are very difficult to uh, to model, and I believe that the combination of hydrologic and hydraulic model maybe can be one of the key. There was a paper that showed the benefits of a 2D model in the Amazon or on the Rio Negro that used this model. The same for the floodplain in the lower Amazon, where actually satellite extent, not volume, have been used there, but can help like hydraulic model to properly route the water, and most importantly to keep it at a good residence and time. Release water fast into the team. Otherwise, you lose this one.
Yeah,
And
thanks.
here, relevant here, so the dams and reservoir are not well represented
Yes.
in model, and I
Yeah.
think SWOT can help out the modeler to incorporate dams and reservoir in this. And
Exactly.
yeah, all right. There is okay, Paymon, go ahead and ask your question.
Thanks, Makan. Thanks, Fabrice, for the nice presentation. And as MJ
Hi.
said, like always.
Thank you.
And just I follow what MJ just proposed about the contribution of the future work with SWOT in improving what we already have with models. But what I have in mind is the tools of satellite altimetry and imagery, even before SWOT, was available for a long time. Why and what hindered modelers to improve their model, and why SWOT can improve these models tremendously? So because what you showed in the result was a huge underestimation of the surface water estimation by models. Is it because they just calculate that as a residual? They missed something? Because it was not the case with soil moisture. With the soil moisture, we saw that even if you use models still, they were at a good range, that in the end the result was not that off. Although that you showed that the contribution of soil moisture was 25%, the surface water 45%. So the magnitude is different, but
I think it's a improper representation of these water bodies still in the model. At least it also depends which model you're using, you see. Because in this case, we compare to be fair, we compare like at least basin scale products to estimates of the model at the basin scale too. So most of the time it's larger. It's a crude also resolution, and the way the water is routed, when you merge like the hydrologic model with the routing model, I believe like the representation of all these channels over the Amazon of these floodplains and how much they contribute to the storage, they are still not properly done. And even in the estimate, I didn't show that, but we still have a lot of differences. I remember the paper of Alsdorf 2010 in the floodplain of the Amazon, where we combined other data set, not using like time varying ones. That was surprising because it was completely off compared to what we knew from models at that time. Well, it was 15 years ago, but still, I think that there is still a lot of uncertainties on the way we estimate that, and then that prevent us from improving the model. And I think over the Congo and the Amazon, because that's regions that we really know, we really underestimate also the quantity of water which is under the forest. So that's something that maybe we should investigate at some point too.
Thanks.
Yeah, thanks. There is a question in Q&A box from Laura Crossetti. Sorry for my mispronunciation. She says, as you have mentioned, it is difficult to validate results, for example, groundwater estimates, because you would need in situ measurement, which are not available. Is there any basin or area available that provides enough in situ data so that you can validate the methods there? And would you wish to have more in situ station? Of course, yes. And is this the limiting key point?
Yeah, I'm a little bit biased because towards the region I'm working all the time, there is no in situ data. And of course, we would like more, but as you know, there's many reasons why there's no in situ data. There have been a lot of studies that have been made in the Mississippi, for instance, in order to derive surface water storage, combining altimetry with other surface water extent estimates from visible. And then they decompose that with GRACE, and they add much more data set to validate that against in situ groundwater storage variation. So it has been done. Over the Ganges, it's been done also. There was no, there were a little bit of in situ data available. So yes, there are regions where you can do that. We haven't tested that because of my bias toward the tropical regions, but it's something we can investigate, that's for sure.
So
and of course,
so in Amazon, you are not running it for collecting the in situ groundwater data.
We have put a PT and a pressure transducer in a well in the middle of the Amazon that we need some time to collect with my colleagues. It's a place in a family village. So hopefully we will have some insight of what is happening under the water of the village. But this is there is no network of groundwater for the moment in the Amazon. That is not there's some and even though again there is such a difference in space and scale to compare what we derive for the moment to such a point that this also limits, even if you have in situ data, this limits the veracity of your results. Yeah, that's for sure.
Yeah, the Mississippi Basin, the USGS running, collecting lots of groundwater data.
Yeah, but I guess by the way, some German colleagues did a lot of studies in the Mississippi.
I'm not sure anymore they are collecting data. The USGS running the network.
Yeah, same. But there were, of course, all the papers from Rodel, where they are in the Mississippi, even in North America. There have been other techniques that have been evaluated against in situ.
All right, great, thanks. Since we are running out of the time, I ask one single quick question, and then we can close the session. So my question is about that you're using multi-mission altimetry, and from one satellite mission to another satellite mission, the ocean scientists have observed some bias, right? And is this the case? Is the bias relatively large, for example, for surface water or water within land, or it's very small with respect to the variability?
Yeah, there is a bias, of course. So we try to correct that, especially with Mohammed. We have a project on trying to estimate discharge over the long term. So for that, we have to build long-term time series of altimetry. So there are several techniques to do that. The ideal one would be also to have a point of reference on the ground. But these biases are due to several stuff also. And the altimetry, most of the time, they don't pass at the same, exactly on the same virtual station because of the cross track. So you have also effect of the slope, effect of the geoid, many things like that. But we are trying to apply techniques to remove this bias, or at least correct them when it's possible.
Right. Okay.
But they can be from a 5 to 30 centimeter, like.
Yeah, it's big.
Yeah, that's huge, and that's a
Alright.
serious concern when you
Yeah.
want to use altimeter for a longer time period.
Mhm.
It's a good point.
All right. Okay, so thanks, Fabrice, again for your
Yeah,
nice
thank you for
overview
asking.
talk. And I think your talk is super useful for our community, but in particular for
Yes.
our working group. And I hope to see you soon, somewhere perhaps in Sweat Science meeting.
Yeah, sure. I'll be there.
Yeah, thanks, Mohammed,
See you,
and
everyone.
everyone.
Thank you very much.
Cheers.
Bye-bye.
Bye-bye.
Bye-bye.